Okay, so thank you for having me here today. My name is Mariya Romanova. I'm a postdoc at Professor Sobolchek Group at University of California, Santa Barbara. And our group is actually working on developing theoretical approaches where we combine stochastic algorithms and many-body perturbation theory to enable accurate quasi-particle energy calculations in very large systems. And today I'm actually going to use twisted bilayer graphene as a demonstration of our methodology. So my talk is entitled Stochastic Many-Body Calculations of Moiré states in twisted bilayer graphene at high pressures. And well, this is the last day of the workshop, and I actually don't have to introduce you the physics of the twisted bilayer graphene, but I really would like to acknowledge the discoveries that motivated this work. And first one is, of course, the discovery of the correlated phases in the magic angle twisted bilayer graphene, which are coming from these flat bands, which in turn are created by the localized states in the Moiré pattern. And the second discovery is that the same correlated phases can be discovered when we apply a pressure to larger angles. And finally, it's also important that screening can affect interactions or these correlated phases drastically. And there was a very nice study by Goodwin who showed that the screening, when we move in towards the correlated regime by decreasing the angle, screening actually reduces the on-site interaction drastically. And while there was the study of the screening upon the angle twisting, we mentioned that there was not really a detailed study of this, what happens with screening in the twisted bilayer graphene when we apply pressure to it. So this was the goal of this work. And first of all, it was the methodological challenge for us, because we want to compute the screening effects from first principles in the very large systems. And these are usually very expensive calculations. And of course, we also wanted to answer the questions such as how does the screening evolve under pressure, how it affects the correlations, and whether the mechanism of formation of correlations upon the angle twist is the same as upon the applying the pressure to the twisted bilayer. So in order to answer these questions, we wanted to start with some weakly correlated system and go towards this correlated regime. So we took a relatively large angle of 6 degrees, which had a supercell with around 2,000 atoms. And we had to apply really exaggerated high pressures to it in order to reach this correlated regime. And so today I'm going to show you how we can compute the quasi-particle band structure in such large systems using our stochastic many-body approach. I also will show you our new development, which additionally to the quasi-particle energies allows us to compute quasi-particle orbitals, and I will show you how that compares to the mean field DFT results. Finally, I should say that many-body perturbation theory is, of course, not appropriate to study strong correlations. So in order to access the strengths of correlations, we will be using the Hubbard model, and in particular is the Hubbard U interaction. We will be computing it from the first principles, and I will show you our new stochastic constraint random phase approximation technique that allows to include the effect of screening into the on-site interaction from the whole system of the twisted bilayer graphene in this large supercell. So just a few words about the many-body perturbation theory. In order to accurately account for the many-body interactions, we use the Green's function technique, and we then use the perturbative expansion, where our interacting Green's function decomposed to the non-interacting part and the part which holds self-energy and which contains all possible interactions in your system. And in this particular work, we are going to use the GW approximation to compute the self-energy. Then once we have the self-energy, we now can compute the quasi-particle energies as a correction to some starting point energies. And in our work, you use the DFT Concham energies. We then remove the extension correlation functional from in this equation and replace it with our self-energy exchange correlation. And what is usually done in literature in the GW calculation is that the self-energy is used in a diagonal approximation. But in this work, we also will be computing the contributions of the all diagonal terms. And finally, to compute the quasi-particle orbitals in a similar manner, we construct the quasi-particle Hamiltonian when we solve it in a self-consistent way. So let's go to the results. And here I'm starting from simple density functional theory calculations to model the pressure in my system. And in order to model the pressure, we actually vary in the interlayer distance in the bilayer. And we compute this equation of state using the van der Waals correction in order to accurately capture these interlayer distances. And here below the equation of state, I'm showing you the charge density of the Fermi levels, which are usually responsible for the flat bands in the twisted bilayer graphene. And you can see that we go really to high pressures. And once we go to high pressures, we indeed can see these localizations which are happening in the Moiré pattern. And if I say localizations, we should expect the flat bands. So we compute the density of states, and this is the DFT result. And you can see that, well, indeed, something happening at the Fermi level, we kind of can see the peak formation, but also the whole band structure, when we move to the higher pressures, is basically shrinking. The valence bands and conducting bands are moving towards the Fermi level. So now we apply our stochastic GW calculations and compute the GW density of states. And you can see that while we see a very different picture here, first of all, we can clearly see the formation of the peak when we go to the higher pressures. And overall behavior of the states around the Fermi level is very different from the DFT result. Basically, we see that the opening around the Fermi level is quite larger, and all states are just moving, shifting up in energy. Well, this difference between the DFT and GW calculations tells us that the many-body interactions in this system are important, and in general, including interactions in your system, as it was shown already before with mean-field Hartley calculations, provide better results in comparison to the experiments. So I told you that we are also computing the contribution of the off-diagonal self-energy terms to the energies. I'm not showing it here, but we found that for energies, the contribution was really negligible. But we wanted to investigate further these off-diagonal contributions, and we computed the quasi-particle orbitals. I remind you that we used this quasi-particle Hamiltonian here, and then our quasi-particle psi states were a linear combination of the initial Coulomb states. And here I'm showing you the matrix of the coefficient, which is just shows how your quasi-particle orbitals are mixed with the initial Coulomb states. And actually, here I'm taking a region which consists of 50 neighboring states around the Fermi level, which is about from 0.5 to minus 0.5 electron volts. And you can see that basically for all states around the Fermi level, we really see a diagonal form of this matrix, while only for 8 states at the Fermi level, we see that there is a deviation of the quasi-particle states from the Coulomb states. But if we take one particular state which still has a diagonal like dominating contribution, we can compare it to its initial Coulomb state. And we actually can say that the special distribution of the DFT states and quasi-particle states is very similar. Finally, we now want to access what is the strength of correlations when we go to the high pressure. And as I said, many-body perturbation theory is not appropriate in this case. But this analysis of the quasi-particle energies actually can be used as a tool to identify the region of states which can then be mapped onto the Hubbard model. And this is what exactly we are going to do. We will take these 8 states and we will map them onto the Hubbard model. Hubbard Hamiltonian here, which you all know very well, contains Hopper energy and on-site interaction energy. And if we compare them, and when the U is much larger than the kinetic energy, we will be in the Stoch correlated regime. So in our system, in order to assess T terms, we actually just take, as in literature, the bandwidth of the flat bands. And at high pressure of 100 GPa, we obtain a T in the order of magnitude of 40 milli-electron volts. And then in order to compute the on-site interaction U, and most importantly, to include the screening effects from the whole supercell of the twisted bilayer graphene, we use our new technique, which is called stochastic constrained random phase approximation. And I'm going to show you also what will be the difference of the U parameters if we compute it in the DFT basis set or in the quasiparticle basis set. So here are the results. And first of all, I'm going to show you bare U parameters. And here I start with the ideal bilayer. And actually, nothing much happened in the ideal bilayer when we apply pressure to it. The bare U parameter doesn't change. But now when we go into the 6-degree twisted bilayer, we can see that under pressure, the bare U parameter is changing drastically up to 500 milli-electron volts from 200 milli-electron volts. And I'm also showing you this green shaded area. And this is actually coming due to the fact that, well, in order to provide one single descriptor for the U, one single value of U parameter, we actually average over these 8 states, which I showed you before. But if we compute each state separately, they're actually different. So that's why I'm showing you the standard deviation here. So now I remind you, I told you in the beginning, there was a study which showed that screening increases drastically when we tune in the angle. And this decreases the on-site Hubbard interactions when we move to small angles. So now we were asking ourselves, what happened with the screening when we change pressure in the twisted bilayer graphene? And this is our result, which I'm showing you here with orange dots. You actually can see the screened U in our case increases. While of course there is a strong screening in principle in the system, it's not enough to compensate the bare Coulomb interaction, which is increasing under pressure. And so the total trend in our study is that under pressure, screened on-site interaction are increasing. And this is very different from what has been found upon the angle twist. So finally, I'm just showing you the comparison of U parameters which were computed also in the quasiparticle states. And again, well, this is something expecting if we see that our spatial distributions of the orbitals the same for DFT and quasiparticle states, they also giving us the same U parameters showed here with violet circles. So now it seems it's not a problem to compute the screening effects in the large systems. This is, however, a problem how to assess the correlations in this system and how your system was downfolded on this Hubbard Hamiltonian. And actually, I just wanted to say that our theory allows us also to extract the frequency dependence of the on-site interaction. However, so far there is no mathematical tool which allows you to solve Hubbard model with U parameter with a frequency dependence. And maybe this could be pursued in the future, and maybe could give us some more insights about the correlations. So with this small conclusion, I showed you our new techniques in the stochastic formalism, which allow us to compute the quasiparticle energies and quasiparticle orbitals. And also, we developed a new stochastic constrained random phase approximation that allows us to compute the screen effects in really large systems. And with this, I thank you for your attention, and I would like to thank our funding agencies. Thank you very much.